So we have to look at function approximation and function approximation and eligibility traces. So what do you think would be different when you do function approximation? Right, so remember, all of you remember eligibility traces. So what did we do in eligibility trace? Let us not worry about the forward view because we are only interested in the backward view here. So what did we do in eligibility traces?
We maintain the trace on all the states that we have, and if we are unitary, we will increase the trace.
Right. So essentially this is a record of all the states that you have seen so far, right. So what do you think we should do when we are looking at function approximation?
We should try to calculate the parameter theta of the state we are currently in from the states that we have visited previously.
What do you mean by parameters theta of the state? Theta is not dependent on the state usually, right?
Value function of the v pi is common.
Yeah, so you have phi times theta, right? So phi transpose time theta if it is linear. So some function that translates the state into a representation which is denoted by phi, and then we have theta, right? So should the eligibility trace be on the phis? Earlier we had eligibility trace on the s, right? Should the eligibility trace be on the phi or should it be on the theta? Phi. How many of you say phi? 1.5. Okay, either put your hand up or down, don't put it here like this. Okay, 2, 3. How many of you say theta? 1, 2. Hisham, you can't put your hands up for both. You put it up. Okay, you did not put it up for phi, is it? Theta. Okay, so why do you say theta? Which entity, right, needs its value to be updated, right? So one way of thinking about it is that you are going to attach it with the phi, right, but then you will have to worry about how the phi figures into your update. Suppose it is a linear function approximator, how will the phi figure in your update? Right, it is phi times delta, right, it is phi delta, right. Now if I put a eligibility trace on the phi, it becomes phi e delta, right. So is that fine, or do you want to do something else? If you put it on theta, then what would happen to it? So for if you are looking at the linear case, okay, it really does not matter whether you are tracking phi or whether you are tracking theta, right, they are almost interchangeable, right. In the linear case, phi and theta are all fine, you can either track phi or you can track theta. The interesting part comes in when you are having non-linear cases where you will have to compute the gradient with respect to theta, right, and then you are going to update the values of theta based on the gradient that you have computed, right. So what does the gradient tell you? Forget about eligibility traces, what does the gradient tell you in a normal function approximator? People know this, right? Huh? Another way of thinking about it is how much is this particular theta responsible for the output. In some sense that is what you are trying to do with eligibility traces also, right, how much is this state responsible for the final reward that I got, right. So it turns out that the right way to track eligibility here, okay, is not to just remember 1 for the state, or bump it up by 1 if you encounter the state again and so on and so forth, but for every theta keep track of the gradient. I heard gradient from somewhere, yeah, who said gradient? Okay, yeah, keep track of the gradient. As before, your delta is right. Right, think about it, if I use a linear function approximator, so what will happen to this? Huh? Phi, this will become phi. And if I had used a lookup table representation for the linear function approximator, right, remember I said an indicator function, right? So if you use an indicator function, it will be 1 for that state that was visited, 0 for it just exactly reduces back to our original TD lambda case, right. So it will be plus 1 for that state that you visited, 0 everywhere else. So this is the accumulating trace equivalent for this. Okay. So let's do control with function approximation, right. So what are the things we need to be careful about? We have to take care of when you are doing control with function approximation. So let us start. So you have to do q of s comma a, you have to keep track of q of s comma a and then you can do SARSA, you can do q learning and so on and so forth. Let us take SARSA is right, doing SARSA with function approximation. So what are the things that you need to take care of? Before that itself, see, we are feeding states and actions into the function approximator and we are going to get a q value outside, right. So what would that mean? When I wanted to feed the state into the function approximator, we thought of an encoding for states, right. Now I want to feed states and actions into the function approximator, I need to think of an encoding for the actions as well. So that is the first thing we have to think about, I need an encoding for the actions as well, right. So instead of looking at phi of s, right, I also need to look at phi of s comma a, right. But then often if you think about how the actions are, right, we end up working with a small set of actions, right. If you think of all the grid worlds, it is north, south, east, west, right. So the number of actions tend to be typically small, right, and also all the MDPs that we work with also have small connectivity, right. So each MDP does not go to hundreds of other states, right. From each MDP state you can go to only a few other states. So that these things are more locally compact and you will not have too many actions, right. In that case what you can do is you could do not have to explicitly encode the actions here, you could just have different set of features for different actions. Alternatively, you could have the same set of features for different actions, but I could have a different set of weights for each action. So this is essentially like saying that suppose I have 4 actions, I will have 4 different function approximators, right, but they will be trained in an interlinked fashion. So what do I mean by they will be trained in interlinked fashion? Do you remember the TD error for SARSA, right? So I will have to use q of s prime comma a prime. So when I do the q of s prime comma a prime, I will use the theta a prime network, right, I will use the theta a prime representation, but for q s comma a I will use the theta a. So that error term I will get, I will use for changing theta a, right. So I will be using theta a prime for changing theta a. So they will be trained in an interconnected fashion. So when a changes, the error for a prime will change and so on and so forth. So its training will be in interconnected fashion, but representation wise, storage wise, they will be stored as 4 different networks, 4 different whatever, right, 4 different approximators, right. So that is one way of thinking about it. This is fine for a small number of actions, right. So when you have large number of actions, how will you handle it? Or as Sagar was mentioning, if you have continuous actions like cycling, we talked about cycling, right, cycling has continuous actions, right, or any kind of control algorithm have continuous actions, right? Or think of Go. What happened to game 5? I did not look it up.
AlphaGo 1.
AlphaGo 1 again, is it?
4 1.
Still 1. Yeah. You have to hang on to hopes wherever you can find it. Huh? Yeah, 4-1. I need to read up. Have you been reading the analysis of these games? Anyone? Huh? Slightly. I mean, there are people. I mean, you don't read the Go guys analysis, but there is a website called Go Guru. Okay, he has given a very nice. He talks about this thing. He, in fact, in game 3 commentary, he said there was one point where he started physically feeling sick because AlphaGo played so brilliantly. He said, I have been following game 1, game 2. Yeah, it was not so bad, but game 3 there was one point where AlphaGo made such a brilliant move that he physically felt sick, thinking that this is the last resistance for human beings. I mean, last whole of supremacy from human beings slipping away because the move was apparently so good. So it's such a nice analysis of all the games, right? So it's called Go Guru. So that place is good. So I don't want to go and read what he says about game 5. Anyway, suppose you have lots of moves like Go, right? Do you think it's good to maintain separate function approximator? There's something wrong there, right? Why? Still doing generalization across the states.
But yeah, actions is not.
Yes. So if you think about all kinds of navigation problems we have been talking about, going north and south may not have anything in common, right? I mean, they are probably very different things. It makes sense to maintain different thetas, right? I'll come back and ask you a question where it doesn't make sense even in that case, but in cases like Go where actions also have some amount of similarity between them, right? It really doesn't make sense to not generalize across the action domain also, right? So in which case how will you go about doing it? Huh? Yeah, so you actually do this, right? Anything else?
Computation should be with respect to
If people don't answer this correctly, I am going to leave.
After states.
After states. Right? So that is another way of using function approximation and control, where you don't actually represent what we normally think of as a Q function, right? But if you stop and think about it, values of after states are in reality Q functions, some form of Q function, because they are values of state action pairs, right? Values of after states are actually values of state action pairs, and you are using your after state as an encoding of a state action pair. Implicitly you are doing that. So a couple of advantages of using after states: one, it allows you to generalize across related actions, right? If the actions cause similar changes, right, then similar, right, not same. Why similar? Similar includes same. I mean, it's more than same, right? In the dynamic programming case, it was same changes. Here it is similar changes because I am using a parameterized representation for the after states as well, right? So after state will also be represented as phi of something, right? So similar after states will have same value. So it's essentially actions that give you similar effects, right? Even if they are from different states, right? If they are going to land up in a similar kind of an after state, then you are going to have the same value for them, right? So this allows you to generalize across actions in a nice way. Second thing, what's the second advantage?
How do we allocate the value to the original state action pairs then, because
Yeah, so see, think about how you use it normally, right? So you looking it up from a state comma action, right? So it is not like I looked at the after states and tried to figure out what state action generated it, right? I usually query on a state action pair, and from that it is only a forward computation. I don't typically need the reverse transformation. Okay. So what is other advantage? Yeah, what is the advantage? What's the computational advantage? What's the advantage?
Fewer after states than state action pairs.
Exactly. So what does it mean?
you can get a more across.
Fewer
One memory
parameters.
is- I mean, not memory.
Fewer parameters to estimate.
parameters.
Yeah.
Yeah. So for memory is a non-issue, right? Fewer parameters to estimate. Memory is a non-issue because I mean memory is cheap now. Anyway, you are not going to be that much worse than what you had earlier. So that much better off, right? So it's fine. So fewer parameters to estimate. See, the more the number of thetas that you have to estimate, right? The more data that you need, right? So the more number of trials and so on and so forth. So computationally it becomes easier if your theta vector is much smaller. Okay. So these are the advantages. So when you have a large number, so I put everything in quotes, right? Because we don't know what large means, right? So how large is large? 4 could be large, right? I mean even with 4 actions you can think of using after states, it might work, right? Or it could be continuous, in which case it's an English question.
Can you repeat the question?
I said large could be 4, right? As few as 4 and after states might be a useful thing, or my action space could be continuous, in which case
Is infinite.
number of is not an appropriate term to use. Okay, so that's why I put everything in quotes. Just tell you that I put things in quotes for some reason. Okay, so if it's a continuous state space, I can't enumerate it, right? So saying large number is not, doesn't make sense anymore, right? So if it is a continuous state space, well, can you use after states?
Possibly.
Yes, possibly. Yeah, why? Yeah, okay. Yeah, yeah, that's a variant of it depends. So I like it. Yeah, go ahead. Why possibly?
Because you can have a mapping from state action pairs to another state.
Exactly. As long as you have a forward model, right, that tells you, okay, here is a deterministic component to this, right? So, but it has to be a deterministic component for it to define after states. Which is stochastic component, then it becomes a little tricky, right? So, if you have, as long as you have a deterministic component to your dynamics, and you have a forward model that describes it, you can use after states. Doesn't matter whether it is continuous, your state space can be continuous, your action space can be continuous or discrete, doesn't matter. You can always use this provided you have this deterministic forward model. Okay. So remember what distinguishes after states from state, right? What distinguishes after state from state is that you are assuming that there are deterministic move and nature's moves, right? The stochasticity in the world can be split up into or the transition dynamics in the world can be split up into a deterministic component plus a nature component, right? See, something happens like the cows, right? So you selling cows is a deterministic component, right? And the cows breeding or going older is a stochastic component, right? So you can split it up into 2 components, like so suppose you are looking at any kind of a control system, right? Suppose I want to move this by 3 degrees, okay, I can move it by 3 degrees, that is the deterministic component, and then there is a 0.5 degree noise that gets applied to it after the deterministic component goes, right? I mean, you could think of it that way. Whether that's a valid model of your system is something you have to think about, or in games it is very clear. So you make a move deterministically, then your opponent makes a move stochastically. So its opponent's move is stochastic because you can't read his mind, right? But if you have a good enough opponent model, huh?
It is not that stochastic anymore.
Not that stochastic anymore. What if your opponent is inherently a deterministic player and then you have his model? When it will be easy, okay for you to use that? You add the state of the opponent into your state representation, right? If you say that, okay, I know what this person is thinking now, okay, then that becomes, everything becomes determined. So whenever I make a move, I know what the opponent's response will be also, right? So I can actually plan far ahead into the future and then do variety of things. But okay, that's an aside, nothing to do with this. So when you have lots of actions, so when you do control with the function approximation, you can either do it like this for a small number of actions. So this means I am going to maintain a different function approximator where a is like size of a, right? For each action I do, or I could do this, right? So anything else you can think of, any other way you can handle this? Have you used something like this before? Have you come across this kind of joint feature encoding of states and actions before? Contextual bandits, right? In contextual bandits we have actually looked at joint encoding of states and actions, right? So it's not something new, so we have already seen it before. Okay. So now move on to the next thing that we should be looking at, which is anticipate me, right. That is it, nothing more fancy than that. Okay. So, all of these are accumulating versions. If I want replacing versions of the traces, what will I do? Instead of? I will not do that, is it? Just add the gradient, is it? Whenever the gradient is non-zero. When do I do that?
For that specific, for ST you just use the gradient, for the others you
What is
do
previous?
lambda.
Huh?
For the state ST,
But this is not on ST, right? This eligibility trace is defined on each theta, right? Oh, by the way, the you certainly do not want the theta to be the size of S. It will only be the case when I am using a lookup table representation, right? The indicator variable representation. If I am going to be using anything more compact, the size of the eligibility trace will be the size of the theta vector, not of the number of states. Okay. I have kind of abused the size notation there, but I am pretty sure you guys will understand what I mean, right? The first two size notations are about the length of the vector, and the last one is the size of a set, the cardinality of a set. Okay.
Sir, is that number of components or?
Yeah, number of components. That's what I said by abusing the notation. Yeah, ET is the number of components in ET will be the number of components in theta, not the size of the state space. Right. So, what will be the replacing version of this? It turns out that in general you can't define a replacing version of this. Okay. So, you can do this for very specific cases where your feature encoding is such that you will have ones and zeros only. It not necessarily be the lookup table representation, right. It could be some kind of a indicator function, any kind of indicator function. It could be tile coding, right. It need not be a 1 of n encoder, it could be some k of n encoders, right, whether it is coarse coding or tile coding or anything, but the point is my fees will either be ones or zeros, right. So, whenever my fee is 1, I will replace this to 1, right. Whenever my fee is 0, I will just decay this. Does that make sense? If my representation is such that for every state, right, take some state S, okay, and my phi of S something like this, okay. So, now what will happen is my E of 1 will be this is for replacing traces. If it had been accumulating traces, this would have been so everything outside the blue dabba is for replacing traces, everything including the blue boxes are accumulating traces, right. This is fine assuming that my fees are binary representations like that, right. If it is not a binary representation, say it is 0.3 somewhere, 0.2 somewhere, things like, you could think of saying that whenever the thing is 0, right, just do the discounting. Whenever it is non-zero, initialize it to that value, right, but that becomes a little tricky because you are even if there is a very small sensitivity, say 0.03 or something like that, you will essentially erase the entire older trace and replace it with 0.03, which is a bad thing to do, right. So we do not want that. So if it is like this, it is fine, right, and in fact we looked at a lot of examples in the last class where the representation was binary, right, whether it is coarse coding, whether it is tile coding, right, all of those things had binary representation. So we could essentially, or state aggregation, we looked at state aggregation, coarse coding, tile coding, all of those, they anyway give you binary representation. In such cases we can use replacing traces, otherwise you use accumulating traces, okay. So any questions? Good. So actually going to stop here, and I am going to get back to function approximation next class. I am going to talk about a bunch of other ways in which people have been using function approximation for RL, right. No, I am not going to talk about deep learning yet, but I will eventually get there, right. So maybe next class or the class after I will do that, right. So next class I will talk about least squares methods which people have been using quite widely, and more it is becoming a standard tool in your reinforcement learning repertoire, right. So I would like to talk a little bit more about least squares methods, and then we will go on from there, right, talking about other ways of doing functional approximation, okay.